Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to my class, and we are in module 4, and this module we started in last lecture, and we are learning interference. Now in the last lecture we talked about interference of light, and we also saw the effect of polarization on interference, on the visibility of the interference. Now today we will start from where we ended in the last lecture. We calculated the expression of total irradiance. This equation number 9 we already derived in the last class, where I1 and I2 are irradiances due to source 1 and source 2, which have electric field contribution E1 and E2 at the point of observation P. And this is the interference term. This term we named it as interference term, and it is expressed by I12. Now to remind you, we started with 2 point sources, and from these 2 point sources spherical waves starts, and then they overlap in a region of a space. Now a point of observation P is very far from these 2 point sources S1 and S2. Since the point of observation is very far, the waves which the observer at point P will observe would be plane wave, because the curvature of the spherical wave front, it would become almost infinity. The radius of curvature would become almost infinity, and therefore the spherical wave front would be treated as plane wave at point of observation P. With that assumptions, we started our calculations, and we calculated the total disturbance at point of observation P due to presence of source S1 and source S2, and from that disturbances we calculated irradiance, which is nothing but time average of square of total electric field at point of observation P. Now at various points in space, the resultant irradiance can be greater, less than, or equal to I1 plus I2, and this depends on the phase del. You see that in this interference term we have a cosine term, and due to this cosine term the irradiance I1 plus I2 will be modulated, and therefore the total irradiance at few points in space would be equal to I1 plus I2, and at few places it would be larger than I1 plus I2, and in few places it would be smaller than I1 plus I2. Now the places the total irradiance is larger than I1 plus I2, it will see more intense light. Our total irradiance would be larger, and therefore we will say that these are the regions of constructive interference. Similarly, the places where total irradiance is smaller than I1 plus I2, these are called the places of destructive interference. Okay. Now how to define these points in space or these places in space? Now if cos del is in between 0 and 1, then we will have the condition of constructive interference, and in this condition the resultant irradiance I would be in between I 1 plus I 2 and I max, okay. And I max is maximum irradiance, and what is the maximum irradiance? Maximum irradiance is equal to I 1 plus I 2 plus 2 square root of I 1 I 2, okay. We get I max when del is equal to 0, okay, and this is what it is written here. A maximum irradiance is obtained when cos del is equal to 1, and in this case I max is equal to I 1 plus I 2 plus 2 square root of I 1 I 2. When will we get this maximum irradiance? We will get maximum irradiance when del is equal to integral multiple of 2 pi, which is written here, when del is equal to 0, plus minus 2 pi, plus minus 4 pi, and so on. For these values of del we will get maximum irradiance, okay. And in the case of total constructive interference, the irradiance becomes equal to I max. The total irradiance in case of total constructive interference becomes equal to I max, and when the interference is constructive but not totally constructive, then the value of irradiance will vary between I 1 plus I 2 and I max, okay. Now, for total constructive interference, the phase difference between the two waves is an integer multiple of 2 pi and the disturbances are in phase, okay. And this is very much clear, because if the phase difference is integral multiple of 2 pi, the two fields would always be in phase, because the phase difference between them is one full complete cycle or integral multiple of complete cycle, and therefore they would be called to be in phase. Now, at places where del is equal to plus minus pi by 2, where phase difference is plus minus pi by 2, in this particular case the cosine term would be equal to 0, and therefore the resultant optical disturbance would be I 1 plus I 2. And when will this happen? This happens when the two interfering waves are out of phase by 90 degree, okay. If the two interfering waves are out of phase by 90 degree, in that particular case the resultant irradiance at the point of observation P is equal to I 1 plus I 2. Yeah. Now, if the value of cos del is between minus 1 and 0, then we have condition of destructive interference, and the intensity or the irradiance at the point of observation P would be between I mean and I 1 plus I 2. This is very much clear. If you substitute back the cos delta in this expression, this equation number 9, you will see the variation in the irradiance, okay. Now, what is I mean? Now, to calculate the minimum irradiance, the two waves must be out of phase by 180 degree, okay. And if they are out of phase by 180 degree, then cos del would be equal to minus 1, and then the expression of I mean would be I 1 plus I 2 minus twice of square root of I 1 I 2. Yeah, here we have now minus sign, the intensity is even smaller than I 1 plus I 2, okay. And this occurs when del, the phase difference is plus minus pi, plus minus 3 pi, plus minus 5 pi, and so on. And this particular phenomena where we get irradiance equal to I mean is called total destructive interference. Yeah, observe the wording. Here I am using total destructive interference, and here destructive interference only. Yeah, total destructive means the irradiance is minimum, okay. The intensity at the dark fringe would be least, while in usual destructive interference there would be variation in the intensity, there would be some modulation in the intensity, but the minima would not be as dark as it is in the case of total destructive interference. and similarly with the total constructive and usual constructive interference. Okay. Now, consider a special case when the amplitudes of both the waves are equal, that is irradiance I 1 is equal to irradiance I 2, and suppose they are equal to I naught. Okay. In this particular case, equation 9 which we derived in the last lecture, which is given here, this is our equation 9. In this equation, if we put I 1 is equal to I 2 is equal to I naught, then the resultant irradiance I can be expressed by equation number 13, and which says that I is equal to 4 I naught cos square del by 2, and let us calculate the I max and I min for this particular case. The irradiance would be maximum when del is equal to del by 2 is equal to 0 or del is equal to 0, and when del is equal to 0, the maximum irradiance is equal to 4 into I naught. Similarly, the minimum irradiance will be equal to 0 and other values which we already discussed. Okay. Now, let us plot equation number 13 and see the variation of irradiance at the screen. Now, if you plot del by 2 here on the horizontal axis and I by I naught on the vertical axis, then you see that the intensity maximizes when del is equal to 0, and then it goes to, it reduces down, and then it goes to 0 when del by 2 is equal to minus pi by 2 here and pi by 2 here and positive, and then it again goes back to its maximum value, and then again it goes down, and then again it goes up, and this again goes down, and this repeats on the other side also. Yeah, this type of periodic variation would be observed. Yeah, if we plot equation number 13, and these are nothing but our interference fringes. Yeah. Now, through these derivations or through this analysis, we found that if we have 2 point sources and a point of observation P which is very far situated from the point sources S1 and S2, then we observe a interference pattern, and where we will see maxima and minima. Okay. Till now we were considering that the waves which are arriving at the point of observation P are plane, but what will happen if we put the point of observation P close to the sources, or alternatively what will happen if the waves reaching at point P, the observation point, are spherical, not plane. Now, in case of a spherical wave, we will have to rewrite the expression for our field, the field which reaches at the point of observation P. Okay. Now, here for spherical waves emitted by 2 sources, we have rewritten the expression for E1 and E2. What are vector E1 and vector E2? These are the contributions from sources S1 and S2 respectively to the result, to the disturbance at point of observation P. Now, since the wave is spherical, the wave front is spherical, the amplitude here is now a function of R1. Similarly, the amplitude here in the second field expression is also a function of R2. They are now function of distance, function of radial coordinate. Yeah, and observe here too, in this exponential part, earlier it was vector k dot vector r. Yeah, we were having 2 sources and we were having point of observation P here, as this is S1, this is S2, and the waves starting from S1 and S2 are reaching to point P. Now, this is R1 and this is R2. Okay. And the k is also in the same direction. Okay, because in the spherical wave, the radial vector and the wave vector would be in the same direction. Okay. Now, since the wavelength of the 2 waves are the same, therefore, we will omit this subscript 1 and 2 from the expression of k. Now, if we take k dot r, now since both k and r are pointing in the same direction, we will get scalar k into r1, yeah, because they are pointing in the same direction. Therefore, k dot r would be equal to k into r into cos theta. Theta is the angle between the two, and theta in this case is equal to 0. Therefore, instead of writing things in form of dot product, usually scalar multiplication is written here. The usual is scalar multiplication. Multiplications are replaced here with the dot products are now replaced here with usual multiplication. Okay. As usual, omega is the frequency of waves starting from S1 and S2, and epsilon 1 and epsilon 2 are the initial phases. Okay. Now, R1 and R2 are the radii of the spherical wave fronts overlapping at P, quite clear. Then therefore, the resultant phase difference would now be written in this form, yeah, del is equal to k in bracket R1 minus R2 plus epsilon 1 minus epsilon 2. Yeah, equation 16 represents the effective phase difference between the waves superimposing at point P. Okay. Now, let us consider that the sources are of equal strength and they are very closely spaced. Okay. Now, what we are doing is that we pick two sources and the separation between the two are reduced. Okay. They are reduced in such a way that the separation between the two sources is much smaller than the distance of point of observation P from either of the sources. Okay. And if this is the case, and if sources are of if the sources are of same strength, then we can safely put E1 E01 vector E01 is equal to vector E02 and I1 is equal to I2 is equal to I naught. I repeat, here we are assuming that sources are very closely spaced and point of observation P is situated at a distance which is much larger than the separation between the sources, and interference pattern is observed around the center of the screen. Okay. The observation space of the interference pattern is quite confined. Okay. If these are the source and this is the screen, then we are confining ourselves in this shaded region around P. Okay. If we consider this, then we will again go back to equation number 13. We replace the expression of del, and this is what we get, the expression for resultant irradiance at the point of observation P. Now, here we see that the irradiance is now function of R1 minus R2, okay, and of course, it is a function of the difference between the initial phase. Okay. Now, moving ahead, we can easily calculate the conditions on maxima and minima. Maxima occur when del is equal to integral multiple of 2 pi, where m is equal to 0 plus minus 1 plus minus 2, basically integer, and similarly minima occur when del is equal to pi m prime, where m prime is plus minus 1 plus minus 3 plus minus 5 or so on. We can relate m and m prime with this relation. Yeah. In the second case, del is odd integral multiple of pi, while in the first case where we are seeking maxima, del is integral multiple of 2 pi. Yeah. Now, with this, like let us substitute del back into equation number 16. Yeah. These expressions of del are substituted back in 16, and once we substitute them back, then we get these two expressions for maxima and minima respectively. Yeah. For maxima we get this expression, and for minima we get this expression. And you can see that on the right hand side it is a constant. On right hand side of equation 18 and 19 we have a constant quantity. Now, if we plot equation number 18 and 19, then we get hyperboloid of revolution. which are shown here in figure 2a. Okay. And for different values of m, we get different hyperboloid of revolution. Okay. Now, in this figure, S is source 1 and S2 is source 2. Yeah, S1 and S2 are the two sources which work as foci of the hyperboloid of revolution. The right hand side in equation 18 and 19, they represent the difference between the vortices in the hyperboloid of revolution. Okay. Now, if you vary m, like this hyperboloid of revolution is for m is equal to 1, this hyperboloid of revolution is for m is equal to 2, this is for m is equal to 0, similarly this is for m is equal to minus 1. Okay. Keep varying m and you will get different hyperboloid of revolution. Okay. But with common foci. The sources, the point sources S1 and S2 here in this particular case works as foci, and any point of observation P, it is at a distance r1 from S1 and r2 from S2. Okay. This is how they are defined. Now, you see that when m is equal to 0, we get a plane which is passing through a point which is at an equal distance from vortices of the two hyperboloid. Okay. And as we increase the value of m, then we get different types of hyperboloid. Okay. It is a 3-dimensional hyperbola. Okay. Now, these hyperboloid of revolution, these are fringes in 3D, these are maxima. Yeah, this hyperboloid of revolution here, they are plotted for equation number 18. A similar hyperboloid of revolution you will get for equation number 19. The 18 represents the maxima. Okay, these hyperboloids of revolution are locus of points where intensity or irradiance maximizes. Okay, and these are the 3D fringes. The interference is happening in space in 3D, and the dark and bright fringes are forming in this 3-dimensional space. And if we trace the bright fringes, then these hyperboloid of revolutions are formed. Okay. Now, if you cut this hyperboloid of revolution through a plane which is perpendicular to the axis of this hyperboloid, then you will get concentric circles. Yeah, if you cut it through this plane here, then you will get concentric circles. Okay. Here you get circular fringes. Okay. What do I mean by cutting this hyperboloid of revolution? Cutting means if you place a screen which is perpendicular to the line joining the two sources S1 and S2. Okay, this is the line joining the two sources S1 and S2, and this screen is placed perpendicular to this line S1 S2. Okay, if we place a screen in this way, then at the screen we will get fringes which would look like this. The fringes would be concentric circles. Okay. Alternatively, if you cut this structure through a plane which contains the line S1 and S2, what do I mean here is that if you cut this structure with this plane, okay, which contains the line S1 and S2, then you will get this. Okay. Now, here you can clearly see that source S1 is sitting here, source S2 is sitting here, the point of observation P is here, and this is your vector r1 and vector r2. Okay. These white lines are the bright fringes, okay, which you observe when you cut the hyperboloid of revolution through a plane which contains this S1 S2 line. Okay. And these circles which you see here on sides, these circles are observed when you cut it through a plane which is perpendicular to the line S1 and S2. These are two different type of fringes. Now, this fringe, the central fringe, which is a straight line, this is for m is equal to 0, the next one is for m is equal to plus 1, the next one is for m is equal to plus 2 and so on. Similarly, here on the other side, this one is for m is equal to minus 1, this one is for m is equal to minus 2 and so on. Okay. Now, you see that close to m is equal to 0 line, there are so many fringes, there are so many dark fringes which are very closely spaced and they are very close to m is equal to 0 fringe. Okay, why is it so? Because our wavelength is very small, okay, and therefore you see almost parallel fringes here in this region, okay, and this is what exactly we observe in Young's double slit experiment. Okay. Now, as I discussed earlier, either one of these equations, which equations? These equations, equation number 18 and equation number 19, they defines a family of surface, each of which is a hyperboloid of revolution, okay, and the foci are located at sources S1 and S2. Now, let us consider a particular case when the two sources, the waves which are emanating from the two sources are in same phase. Okay. If they are in the same phase, then epsilon 1 minus epsilon 2, which is the phase difference due to the initial phase, it is 0. Okay. Then the equation 18 and equation 19 will become this R1 minus R2 is equal to m lambda, and for minima R1 minus R2 is equal to m prime lambda by 2. Yeah, they become quite simple, and if you plot it, you will again get hyperboloid of revolution. Okay. Now, here we saw that irrespective whether we are having a plane wave front or a spherical wave front, we are getting fringes. In spherical in interference with a spherical wave front, we get hyperboloid of revolution. Now, depending upon the orientation of our screen where we want to observe the fringes, the shapes of the fringes vary. Yeah, sometimes we see straight line fringes, sometimes hyperbolic fringes, sometimes concentric circular fringes. Okay. Now, few takeaways from this analysis are: if two beams are to interfere to produce a stable pattern, they must have a very nearly same frequency. These are the prerequisite to observe beautiful fringes. Okay. Please observe on the wording, beautiful fringes. Yeah, interference will happen anyway, irrespective whether the sources are coherent or not, irrespective whether their frequencies are very close to each other or not, irrespective of their amplitudes. Yeah, the phenomena of interference will always happen, it would always be there. Okay, because the waves are anyway overlapping, but to observe beautiful fringes which does not vary with time, we must have a very nearly the same frequency. The two sources must have almost same frequency. Okay. A significant frequency difference would result in a rapidly varying time dependent phase difference. And how would it affect our fringe pattern? Now, if the phase difference is varying very rapidly, then the positions of maxima and minima will vary. Okay. And if these positions varies, then over if you take time average, then you will see a uniform illumination on the screen. We would not be able to detect distinct fringes. Okay. And this is what it is written here, which in turn would cause I12 to average to 0 during the detection interval. Okay. And therefore, a uniform illumination would be visible if the frequency difference between the two sources is large. Okay. Second takeaway, if the sources emit white light, the component reds will interfere with reds and the blues will with blue, producing observable interference. Okay. whenever we talk about interference, we always tell that the source must be a coherent source, yeah, and the second criteria is that the phase difference between the interfering waves must be constant throughout, okay. But here what we are claiming is that even with the white light we will be able to observe interference fringes, and we will talk more about white light interference in forthcoming lectures. The next point is the clearest patterns exist when the interfering waves have equal or nearly equal amplitudes. Why? Because when it is constructive interference, the wave's amplitude will sum up and a very nice bright fringe will appear, and when it is destructive interference, all the energy will go away and we have very nice dark fringe, and due to this nice contrast the very clear pattern would exist, okay. And therefore, if we want to observe a very nice beautiful well contrasted interference pattern, the waves must have almost equal amplitudes. Next point, for a fringe pattern to be observed, the two sources need not be in phase with each other, okay. The important point is that the waves emanating from the two source must maintain the constant phase difference, okay, irrespective of the value of this constant, okay. If the phase difference is 0 initially, you will observe well beautiful interference fringe and it is symmetric, but what if the phase difference is not 0 but constant? If it is not 0 but constant, then a somewhat shifted but otherwise identical interference pattern will occur, okay. And if there is some initial phase difference between the sources, then there would be a shift in the interference pattern, okay. But if it is a linear vertical lines, then this shift would be indistinguishable, okay. And as long as this initial phase difference is constant, you will see a nice bright and beautiful interference pattern, and this shift would not matter, okay. Whatever applications of the interferometer have, it would still be able to satisfy those applications, but the fringe pattern would be a bit shifted due to non-zero value of this constant phase difference, okay. Now, if we have two sources and the phase difference between the two is constant, then such sources are called coherent, okay. If the two sources maintain constant phase difference over a long period of time, then these sources are called coherent sources. We will discuss more about coherence in our forthcoming lecture, okay. The next point which we observed is that two orthogonal polarization state cannot interfere in the sense that I12 is equal to 0 and no fringes result, okay. During our analysis we saw that if we let interfere to cross polarized light or to cross polarized wave or the waves which are orthogonally polarized, then the interference term is equal to 0, okay. And when interference pattern is 0, then you will see a uniform illumination on the screen on the observation plane. We will not be able to see fringe pattern, although interference is happening there too, but due to this cross polarized nature of the interfering wave, the fringes will not be there, okay. Now, the locus of closely spaced sources S1 and S2 when displaced vertically normal to the S1 and S2 line is two narrow slits, okay. We started with two slits S1 and S2, okay. This were the two slits and this is the line joining the two slits. Now, if we shift the position of these 2 point sources S1 and S2 along a line which is perpendicular to the line joining S1 and S2, then these point will either go up in this direction or in this direction, okay. But if this we shift the position of these two sources vertically, then what will happen? Let us go back. Now see figure number B 2b. Now if you shift S1 and S2 vertically up or down, then what will happen is that the whole fringe pattern will either go up or down. Yeah, if S1 and S2 are shifted vertically up, the whole fringe pattern either will go up, and if the S1 and S2 are shifted down, then the whole fringe pattern will go down. Okay. In this exercise, the position of almost vertical fringes which are here sitting at the center, they will remain unaffected. Okay, they will remain intact. The distribution at the center would almost remain intact. Okay, there would not be any change. Okay, and therefore, what we can do is that we can create a line source just by shifting these 2 point sources S1 and S2. Let us consider several S1 and S2 and put them along a line. Then S2 will create a line source and similarly S1 will create a line source. Okay. And then if you generate interference pattern out of these line sources, then we will get these vertical lines at the center, but since the number of sources has got increased, the irradiance of these bright lines would be larger, yeah, because the number of point sources which are contributing in the formation of this pattern has increased, and this will also therefore increase the irradiance or the brightness of the bright fringes, the bright vertical lines. Yeah, and this is what exactly happens in Young's double slit experiment. Yeah, and this is what is also written here. Locus of closely spaced sources S1 and S2 when displaced vertically normal to S1 S2 line is 2 narrow slits. Okay, this will create 2 narrow slits which generates larger number of aligned fringes. Yeah, the central fringes will be generated and they would be large in number and with increased irradiance. Okay, the irradiance will of course be increased because the contributing source has increased now. Yeah. Now this is all for today. Yeah, today we discussed in detail the basics of interference. Okay, and in the next class we will talk about Young's double slit experiment, the famous experiments on interference. Yeah, thank you all for listening me.